Good morning, everybody. Good morning, Ruben. Good morning. Welcome to a sunny but cold morning of Chem 1105 with your host, me, Dr. White. All right, some important things. One, this Friday, I will be giving test number 3 online, just like I've done the rest of the tests. Sometime Thursday, you'll be able to download uh, both versions, so you'll be ready of test number 3. And then right about 10 o'clock or a little before on Friday, I will send out an email with your password for your version of test number 3 you're going to take. Now, if we were face to face, test number 3, I give students 50 minutes because they have to be out of the classroom in 50 minutes most times because there's another class behind, but you're going to get extra time. Why? Because you'll have until 11:30 to take test number 3, scan it or take a pictures, whatever, and upload your answers as a single PDF file to Blackboard. So that will be Friday. This Wednesday, I will give my world famous review for the next test, test number 3. So stop by. Also, I'll have a video for it. Now, one of the things I grade labs this weekend, like I do every weekend, and some of you are having a lot of problems with the calculations, especially molarity. Therefore, tomorrow, before lab, what I will do is I will go through some important calculations that you should know how to do. Hint for test number 3. So make sure you stop by or watch the video. Some of you, nobody's been watching my videos. It's not my breath. Oh, wait, you can't smell it. But anyways, let me know, is there any problem you watching the videos or seeing them? But anyways, that's what I'll do tomorrow. Also, instead of, I was thinking about what to do today, instead of going through some practice with conjugate acid bases, I'll do that tomorrow. Plus, we'll have a lab, and that lab we'll use beyond Lab Z. And the other thing I have to do because of my upcoming operation a week from today for my cataract on this eye, then 2 weeks later will be this eye. But anyways, sometime next couple by Saturday, for sure, I'll be making a video for next Monday. Now, I always give back and go over the test, the next class after a test, but I'm not going to be here next Monday, so you'll be able to watch a videotape. Therefore, on the Tuesday, if everything goes well with this, I will go through the answers then. Sorry about that, but as they say, life happens. All right, any questions before I get into some good acid-base stuff? All right. I realized I didn't have slides for the following, so it's time for doing it the old-fashioned way, writing it on the whiteboard. Now, there's something called acid-base neutralization reactions. I think I spelled neutralization correctly. But anyways, if you take any acid and react it with a base, an acid is a proton donor, a base is a proton acceptor. So you get a proton transfer. And essentially, if you think about it, cation, anion, you get a salt. And this is called the neutralization reaction. Why? Let's remember, by the way, I didn't ask, and last week it happened once or twice. Thumbs up, people. Can you see acid-base neutralization on your screen? Thank you, Spencer. Or no, I'm sorry. Well, yes, it was Spencer. And thank you, Ruben. All right. Now, if you have an acid, the pH is going to be below 7. When you add base to it, it's going to react, and there's going to be less hydrogen ions, and the pH will go up toward neutral. If you add more base, it goes beyond neutral. And that's why they call it a neutralization reaction. Now let's look at a couple. If I take hydrochloric acid, HCl, and sodium hydroxide, NaOH, HCl is an acid. You should know this for test number 4, not 3. Remember, test 3, I've already put what it will cover, but it covers gases and solutions, but we're going through stuff for test 4. So HCl, hydrochloric acid, sodium hydroxide is a base. And what you get, proton transfer, you get HOH, water, and you have Na plus Cl minus, which come together to form salt, nickel. Remember, please pass the nickel. And when you do this, the initial pH of the HCl is low, and then it goes up as you add the base. This is called neutralization. Now, an interesting, you did that in the food lab. Now, let's look at something interesting. And by the way, everything I'm talking about, the switch is on. This is any acid. This is sodium bicarbonate, a base. And when you do this, you get some interesting results. You get Na plus, A minus, plus water, plus carbon dioxide given off as a gas. What happens? Well, the proton transfers over here, and you get Na plus when you add sodium bicarbonate. This part underneath, ooh, I'm having a bad arrow day, sorry. Anyways, you don't have to know this part, you should be familiar with. All right, you have proton transfer, so you get Na plus, A minus. I don't have to show the charges, but I'm showing you. And you get this compound. I'm putting it in brackets because you can't isolate it. This is called carbonic acid. But if I draw the structure, I'm going to give you some organic here. This is inorganic. Oops. That's what that is. And if you notice right here, in here, I have H and an oxygen, OH, and a hydrogen there. What's two hydrogens and one oxygen? Two hydrogens, one oxygen, H2 and an O. It's water. What happens is this dissociates to water, and notice what's left behind. Two oxygens and a carbon, CO2. And whenever a molecule has good leaving groups that are stable, and water and carbon dioxide are, it just boop falls apart. And that's why you get this. Have you ever wondered why Dr. White, me, became a chemist? Well, it started early on. It's time to tell a long time ago story about me. Back when I was about way young, about 5, 6 years old. First of all, when I was that young, the big thing in the United States was the space race. United States against the evil Soviet Empire. And they were evil, they still are today. But anyways, that's another story. But the big thing for little kids in the United States was anything to do with a rocket. And when I was a kid, it was about this big. They had a candy, these little beads, that was the most disgusting, awful candy you've ever tasted. And I'll explain why. And it was in this little tube with a cap that had fins, and it was a little rocket ship. And they were like a penny a piece, real cheap, inexpensive. And I had them, my friends had them. Oh, by the way, warning, Dr. White artwork. Don't laugh too hard so you injure yourself. But these rockets look like this. Here was the tube. It had a cap with 3 fins. And inside were these little dots. And you pull the cap off, turn this upside down, pull the cap off. Supposedly you ate the candy, put the cap back on, which was now empty, and you had a little rocket ship to play with. Well, how do you know this was really bad candy? Well, I and my friends, whenever we got one of those, we'd open it up, find a garbage can, and dump the candy in there. What 5 or 6-year-old wouldn't eat candy? 5 or 6-year-old who doesn't like the taste of awful candy, and it was bad. Ugh. But anyways, the rocket ship was fun. Well, my father, being a pharmacist, knowing chemistry, I still don't know why I became a chemist. But anyways, showed me something which I taught my friends, which was the neatest thing in the world. Even today, I still think it's neat. If you take the cap off, you have a little test tube. And these are only about maybe 2 inches high, half an inch diameter. I don't remember the exact. And if you put in some vinegar, and then after that, put in very quickly some baking powder. I think I'm spelling vinegar wrong. I always do. And put in the sodium bicarbonate, put the cap back on, invert it, and hold it by the fins. And unfortunately, I don't have one. I wish I had one. I have other things from my childhood, but not that. You hold it like this, and inside, the acid reacts with the sodium bicarbonate to make carbon dioxide gas. And the pressure builds up, and all of a sudden, pop, the cap, that plastic tube fires off, just like if you were blasting your own rocket. If your timing was good, you could make it fly about 3, 4, 5 feet even. And we'd just go get vinegar and baking powder and just have a lot of fun doing that outside. Don't do that in the house. Well, it turned out my best friend back then, I haven't seen him in decades, Dickie Gale, he moved out of the state long ago when I was little, but he and his brother and I were out playing with our rockets, and we used up all his mother's baking powder. And later that day, or after the early afternoon or whenever, she went to do some cooking where she needed that, and the can was empty. Boy, did he catch it. Boy, oh, did he catch it. So if you ever do that, don't use up all your mother's baking powder without telling her she needs more, or better yet, buy some more. And that's a true story. And that's all because of a neutralization reaction. And the neutralization reaction was acid, which vinegar has acetic acid, reacts with sodium bicarbonate to neutralize it. But when it does, it forms CO2, carbon dioxide gas. How do you know? That's what the arrow is. And that arrow up tells you it's a gas. It even says it on the screen. But anyways, that's one thing. Now I'm going to tell you another story. Uh, I have I have two sisters, one 7 years older, one 7 years younger. I truly am in the middle, really. And uh, my father, my mother was a very good cook. My father was a better one. And back when I was a kid, men didn't cook. Even today, a lot of men don't cook. Well, anyways, he had a drugstore, pharmacist. Years later, when the chains started coming on, like Walgreens and others, he sold it and became a pharmacist at a major hospital and other hospitals too. But anyways, back when he had a drugstore, he worked Monday through Saturday. Sunday, the store was closed. So some Sundays he'd say, all right, this Sunday, it's men only cooking in the kitchen. He kicked my sisters and mother out and stay out. We're cooking together. It was the way we bonded together. And one of the favorite things he liked to make was spaghetti sauce. Now, from the time I was a small kid, 5 or 6, my parents had this huge chest freezer separate from the regular refrigerator freezer. And we kept that stocked up. And even to this day, I have now a huge stand-up refrigerator, freezer, I mean, besides my refrigerator freezer in my utility room, that's pretty stocked up too. So anyways, when he would make spaghetti sauce, he would make a big pot. We're talking about maybe 3-4 gallons. He had those size pots. And one of the things that one of the regrets, I never asked him, how'd you figure this out? I just, learned it. And, oh, that's how he does it. All right, when he'd make the spaghetti sauce, he would do the tomatoes and sauce and all that, and spices, onions, garlic, and all that. But he cut back on the salt. And near the end, after it'd been cooking a while, he would add, don't forget, we're talking a huge pot, about a tablespoon and a half of baking powder. And you see this white foam on top, and then you mix it after a while and disappeared. What was going on? Well, tomatoes, whether it's tomatoes, tomato paste, or tomato sauce, all contain an acid, and that's citric acid. And if you've ever had a canker sore and you have ketchup, you go, ooh, that doesn't feel good. That's because the citric acid is interacting with your canker sore. Acids can cause discomfort or worse. Citric acid is a very mild, weak acid. So what was going on? Now, when he added this, plus the sodium bicarbonate, you had an acid-base neutralization. This is an acid, this is a base. And what you get is a salt. It's called sodium citrate. I'm not going to write the structure. And you get water. And that foam was, oops, was because of the CO2 being given off, forming bubbles that were rising in the tomato sauce because it was thick. And this has a salty taste. So that's why you cut back on the amount of actual sodium chloride you put in there. Now, what did that do? It neutralized some of the acid, raised the pH, and made it taste milder, smoother. Now, true story. In one of the classes I was teaching, this organic chemistry, I told the same story because we go through citric acid. And the question, how do you do it? Why does this happen? And I told that story, and I'll give you another hint too, or tip on making the best spaghetti sauce. I said, don't put too much in, but enough. So about 2 or 3 weeks later, one of my students came to me and said, my father and Lila would like to thank you. We made that spaghetti sauce with your 2 tips. I've told you one. Hang on, I'll tell you the second one. Remember, that's sort of a mini secret. No, not really. But anyways, she said, thank you. I said, well, you're welcome. What are you thanking me for? Well, my father and I suffer very badly from acid reflux. That's where your stomach acid gets up into your esophagus. I worked at one company where another manager had it so bad, he actually had to have an operation to fix things so it wouldn't give him so much pain. And she was telling me, we love spaghetti sauce or spaghetti and meatballs with spaghetti sauce, but when we eat that, because of the acid in the spaghetti sauce, it gives us a lot of pain. Well, when you neutralize it, like you just showed us with the sodium bicarbonate, we didn't have that pain. Thank you. I thanked her. Now, the other secret, not really, I don't know how my father found this out. Have you ever made your own spaghetti sauce? And this doesn't taste the same as the good spaghetti sauce at those really fine restaurants. And what's different? Well, they add a pinch of cinnamon. In the big 3-gallon pot, my father had maybe 1/8 of a teaspoon of cinnamon. If you add too much, you just taste the cinnamon. But that little pinch of cinnamon gives it that special secret oomph or flavor that makes it taste like the professional. I don't know how he found that out or experimented, but it does. All right. Now, remember, when you have a neutralization reaction, acid plus base, the pH increases or decreases depending on what you're adding or not, or whatever. So let's look at the following. I assume everybody can see this on their whiteboard. Let me check with my thumbs up, people. Can you see 2 points each? Thank you. Thank you, Ruben. Thank you, Spencer. All right, let's take a look at this. What happens to the numerical value of a beaker, the numerical value of the, I forgot something here. That makes sense. Now, what happens to the numerical value of the pH of a beaker of water at pH 7.0 if you add a few drops of A, concentrated HCl solution, B, concentrated NaOH solution? You should know. And when you're at pH 7, what is HCl? You should know that's an acid. And when you add an acid, the pH goes down because it becomes more acidic. So the answer for A is the pH decreases. You could also say goes down, or you could put an arrow, goes down. And when you add an acid to a solution of, say, water, the pH will go down. Now, let's look at B. What happens to the pH of a beaker, the numerical value? I'm not asking, does it become acidic or basic? I'm asking what happens to the numerical value of a pH of a beaker of water at pH 7.0 if you add a few drops of concentrated sodium hydroxide solution. Well, you should know sodium hydroxide is a base. And when you add a base, the pH goes up now from 7. It becomes more basic, but I'm asking what happens to the actual numerical value. And the answer is, since that's the base, it increases. Or you could have put goes up, or you could have put an arrow up. And that's something you should be familiar with. If you're at pH 7, whenever you add an acid, the numerical value of the pH decreases. It becomes acidic, but the actual number gets lower. When you add a base to a solution of water at pH 7, the solution becomes more basic, but I'm asking what happens to the numerical value. If you're at 7, it will increase. The closer to 14, the more basic. The closer to 0, the more acidic. And this is a concept you should know. Oh, I haven't done this today, so. All right. Now, the importance of the neutralization reaction can't be stressed. And where do we use it? In something that's used throughout the United States daily. Is called an acid-base titration. And now I'm not talking about the definition. I'll be going through the concept of what is an acid-base titration. By the way, tomorrow in lab, you'll be doing one. And that's a neutralization reaction, which a measured volume of acid or base of known concentration is completely reacted with a measured volume of acid or base of unknown concentration. And this allows you to determine the unknown concentration of the acid or base. Now, What's key about acid-base titrations? First of all, one classic way of doing this is using an indicator, or sometimes called the pH indicator. And this is a compound that exhibits different colors depending on the pH of its surrounding. In other words, the solution it's in. And this allows you to visually tell when it's either slightly acidic or slightly basic. What I mean by slightly is only a couple molecules over either way. It's very accurate. And this, like I said, is also known as a pH indicator. Now, the most common, widely used pH indicator, and I'll never ask you to name, but I will use it in class and in the lab tomorrow, is phenolphthalein. And phenolphthalein changes color at pH 7. If you're 1 or 2 molecules below pH 7, a solution with phenolphthalein is clear. As soon as you go 1 or 2 molecules basic above 7, phenolphthalein becomes a wine color, reddish color, and it's beautiful. I wish you, well, you'll see. I think I have some YouTubes. Let's see something. I'm looking at, see if I have, nope, I don't. Let's do something real quick. Maybe not too quick. All right, let me make sure you can see this. Let me ask my thumbs up people. I don't know if this is a good one. Can you see YouTube phenolphthalein on your screen right now? Thank you. All right, let's have some fun, chemistry fun, Dr. White style.
Experiment of phenolphthalein indicator. Phenolphthalein is one of the indicators which is used in the neutralization reaction, and it is colorless. In 2 test tubes, put 2 equal amounts of phenolphthalein indicator.
We'd use an eyedropper.
And add distilled water to both of them. What do you observe? The indicator's color doesn't change. Therefore, phenolphthalein is colorless in the neutral medium. Add drops of sodium hydroxide solution to the indicator in the first test tube.
Watch what happens.
What do you observe? The color of the indicator turns red. Therefore, the phenolphthalein indicator turns red in the basic medium. Add drops of hydrochloric acid to the indicator in the second test tube. What do you observe? The color of the indicator doesn't change. Therefore, the phenolphthalein indicator is colorless in the acidic medium. Add drops of hydrochloric acid to the basic medium in the first tube. What do you observe? The red color of phenolphthalein turns colorless due to the consumption of the base completely during neutralization process with the acid. Summary: phenolphthalein indicator is colorless in acidic and neutral media, but turns red in the basic medium.
This is a neutralization when he adds the acid to the colored solution. I didn't show it. Was that neat or was that neat? By the way, the color changes because the presence of H plus, the hydronium ion or H3O plus, changes the structure, electronic structure of the phenolphthalein. Notice I don't have an Indian British accent, but is in America we call it phenolphthalein. Now, interesting side note, are you ready for this? Does everybody ever hear of the product X-lax? Anybody ever hear of that? By the way, it's a diuretic. If you are constipated, it helps you get unconstipated. And for many decades, the active ingredient that did that to you in X-lax was phenolphthalein. Till about 15 years ago, they found just the tiniest chance it might be a carcinogen by taking it as a medicine. So they went to another molecule. But phenolphthalein in the lab has amazing uses, and it's used in a titration. Now, titration data are used to calculate the molarity, moles per liter, of an acid or base solution that's unknown. And the key points to an acid-base titration are: at neutral pH, you can calculate the moles of a known molarity acid or base. Based on neutralization reaction, you can determine how many moles of the unknown molarity acid or base was present in the volume of sample of the unknown acid or base. And based on that, you can then go ahead and calculate the molarity. So what that really means is if you know the volume of an unknown acid or base and the moles in that sample, then you can calculate the molarity of that unknown acid or base. Now, what I should have here, which I have in important information test number 4, when the phenolphthalein, for most labs, phenolphthalein is the indicator of use. There are other indicators that change color at different pHs, like at 3, 4, 6, 8, whatever. And for certain tests where you neutralize something with an acid or base, those are useful. But most of the time, in every lab I've ever worked in, we just use plain old phenolphthalein. And when that changes color, that one drop, you know you've neutralized all the acid or base because the pH changes. It's just one, it only takes one molecule. You're not going to get that accurate, but you can get pretty accurate above where you add to neutralize everything. One molecule beyond that, phenolphthalein changes like that. It's quick. You can also do it in a pH meter, which I'll teach you tomorrow, but I like phenolphthalein. It's really accurate. So what does this mean? At neutralization for a titration, moles of acid equals moles of base. Now it's time, and be quiet, don't tell anybody, for a special gift from Dr. White. Now, I haven't talked about different types of acids and bases, but let's just talk about acids. Hydrochloric acid has one acidic proton. This won't be on the test, what I'm doing right now. And this is called a monoprotic acid. Sulfuric acid, H2SO4, has two acidic protons. If I could spell it. Guess what? I can make the same mistake on a whiteboard in front of a group of students. And we call this diprotic acid. In chemistry, the prefix di means two. Well, what I'm going to be teaching you is for monoprotic acids. If we did diprotic, then it gets more complex. And my gift to you today is we'll only do it for monoprotic acids. So let's take a look at what are we really trying to find in a molar acid-base titration. We're trying to find molarity. And molarity, as you know, is moles solute per 1,000 milliliters. So if we go up here at a titration, at neutralization, and right now it may seem, what is going on? You'll figure it out. I'll help you. At neutralization, moles of acid equals moles base. Now, what are moles of acid? That's milliliters. Oh, I forgot. That's milliliters times molarity. And the molarity, oh, someone wrote that up for us, is moles, in this case, acid, because that's what we have on this side, per 1,000 milliliters. And what's moles of base would be milliliters, I should have here acid, times moles acid per 1,000 milliliters. Now, a trick you can pull off with the monoprotic acid, and that's all I'll ever give you, is you can actually just put in the molarity each here. You don't have to put it in as a moles per 1,000 milliliters. So the equation you can use for titration is milliliters acid times molarity acid. Remember, capital M is molarity, equal milliliters base times molarity base. Now, in a titration, you'll have this number, and then one of these And then the other one, you'll solve for it. So if you have an unknown acid, you'll have milliliters of acid, you'll titrate it with milliliters of base, plus you'll know the molarity of the base. And once you titrate it, you'll get this number, how many milliliters you have to add to make the color change. And then you'll solve for this, divide both sides by milliliters, or if it's a base. Now, one of the things that's interesting about acid-base titrations, they're used to determine a lot of different important parameters of chemicals made in chemical plants, and also chemicals made in other places like your personal care products. And a couple of companies I've worked at, every day, the QC, quality control lab, would analyze new products. And one of the ways they would do it was with a titration. In fact, at Unichem Chemicals, we did one titration. And every morning, all the product tanks were measured again. And that was about 75 to 80, depending how many if they added any to the new product tanks, titrations, and that was a lot. So what I did was, there's electronic equipment, you won't use it as an undergrad, that does automatic titrations. And I found a good one. We set up an auto titrator, it's called, and you put your samples in, put it on a belt, or nowadays it's a table, and probe comes down, as in this case, a product unknown was an acid, and would add the base, get a number, and tell us how pure that product was by the titration. And the chemists involved were happy, because doing 75 titrations every morning was not the most exciting thing in the world. And that worked out well. It did get me in trouble, because I was able to figure out that here in the United States, it was an international company, and they had been trying to do that for a couple of years and couldn't. I did, and the research manager, the vice president of research and development in Europe, wasn't happy. Who gave you authority to do this? I said, I solved it. Aren't you happy? He was still mad at me. Unbelievable. It was a classic case of Nih syndrome. How many of you have ever heard of Nih syndrome? Let me check, do something. Let me do it this way. This way I can check quicker. Any of you have ever heard of Nih syndrome? No. Well, it's time for me to teach you something real quick. And guess what I didn't do? I forgot to pin myself. Nope, that's not what I want. Oh. Anyways, Nih syndrome is not invented here syndrome. That's why he was mad. With that, I'm done. I went over. I'll see you tomorrow morning at 9. Do your labs. One's due tomorrow. I have an office hour today. If you have any problems, see me. With that, gang gesund. Goodbye. I'll have to figure out why I can't There we go. With that, gang gesund. Goodbye.